Good morning and welcome, everyone. Thank you for joining us. My name is Emily Manchi, and I'm part of the Stanford CME team. This session is designing and building AI-ready and data and infrastructure. I have the pleasure of introducing our moderator for the session, Dr. Louise Sun from Stanford University. Dr. Sun, I will pass it over to you now.
Thank you, Emily, and thanks so much, everyone, for attending. So we have a good session planned out for us on designing and building AI-ready data infrastructure. We have a number of speakers. I'll be starting off talking about data-driven operational management and how to harness data to its fullest potential. This will be followed by Dr. Kristen Young and Dr. Edward Lee from Stanford, who will talk to us about federated learning in radiology. This will be followed by Dr. David Ouyang from Cedars-Sinai, who will talk to us about building AI-ready data infrastructure in cardiology. And last but not least will be Dr. Mike Mathis from Michigan, who will be talking to us about MPOG data. So I'll do the introductory talk. And this talk is really meant to set the tone for the rest of our session. Can you see my slides well? So
it looks good, Louise.
All right, great, thank you. I'm going to start off by talking about what big data is, and then move on to talk about applications of big data in research and patient care, and then how to harness data to its fullest potential. So first of all, what is big data? Big data is a concept that's been talked about a lot nowadays. And if you look in the dictionary, first you look at the word data, the definition is not so bad. It talks about factual information that's used as basis for reasoning, discussion, or calculation, or information in digital form that can be transmitted or processed. So fairly practical answer. And if you look up the term big data, it'll tell you it's an accumulation of data that's too large and complex for processing by usual or traditional means. And so what big data actually involves is not just the data itself, but also about extraction, validation, storage, transfer, access, sharing, ownership of the data, as well as things to do with privacy, and finally, analysis plan for that data. Traditionally, big data is defined by the three V's: volume, velocity at which the data accumulates, and also variety of the data. And so the landscape here is that we know this is the era of rapid development and application of big data and AI, and there's quick uptake of big data and artificial intelligence techniques in many areas of healthcare. The way I see big data and artificial intelligence in the clinician's life is really to augment the clinician's intelligence as opposed to replacing the clinician altogether. And our colleagues later on during this session will be delving more into that concept. And so what are the types of data? And so first off, I'd like to say that data is the essential building block of information, and big data is the essential basis for digital health innovations. There are many types of big data in healthcare. My list is by no means exhaustive, but it does give you the most frequently occurring variety that you see almost on a daily basis. And so we have population-based administrative data, we have EHR, clinical databases or registries. We have text data, and text, it could encompass a variety of things like clinical notes. It could be any kind of medical pathology reports, imaging reports, and so on. Images are being harnessed as data. And finally, biobank materials will yield a great amount of omics data that can then be used to more precisely phenotype patients. So how data can be utilized? Well, on a population level, so when we're talking about the population-based or administrative type of data, they could be used in real-life epidemiologic studies, in health policy and economics, comparative effectiveness research, and also in making clinical prediction models. Precision-based data also can be used to augment the clinical prediction models in a more personalized fashion, and also to produce molecular and proteomic signatures for individual patients. And so basically, all of these could together enhance personalized medicine. Applications of big data and AI in healthcare. Well, visualization is really where a lot of those things start, and is the most basic element of how we can explore the data set that we have at hand. So descriptively, it helps us at a glance kind of look at the patterns in the data that we have. And at the administration level is very helpful because it gives a high level, or at least in a really basic sense, what's our case volume and what are some of the basic metrics we're looking at. But really what's more important and what's going to inform or drive clinical decision-making is predictive analytics, where we actually go on to use data to produce clinical decision support tools to help with diagnosis and personalized treatment of patients, and administrative data, or just administratively to allocate or plan resources. We could use data for drug and biomarker discovery, to analyze user behavior analytics, to enhance our communication with staff and patients, as well as to improve patient safety. And finally, we know that medical imaging is an area where AI has the most rapid growth. And it's an area where truly AI is being used to augment the clinician's intelligence. So in terms of dissemination methods, and this is by no means an exhaustive list. We know that we have many ways that we could bring data to the bedside in a more rapid fashion, but application development, wearable technology, and integration with EHR are a few places where we're starting to make this happen. So some of the things that I've learned, and by the way, in my previous life, I was the director of big data and bioinformatics research in Ottawa, back in Canada. And one of my main jobs was actually to act as a person that bridges between data scientists, clinicians, clinical administration, as well as information technology, to warehouse data in a creative manner, to harmonize existing data from different sources, as well as to utilize data in such a way that it solves pressing and important clinical and administrative problems. It was a fun job, and I learned a lot along the way. And some of the things that I learned were, first of all, we need to know the data really well. So every time we open up a new data set, it's not just a matter of, asking IT to pull a big bowl of data for us to play with. There's actually a lot more to it. And so we need to know the source of the data, where it came from, the integrity of the data, people who supply or enter the data. Say, is it a clinician who's entering things into Epic, and how reliable by type of clinician or stage of training. People who abstract the data, we need to know how they work and how they interpret the data that they see on Epic or other sources where they extract it. And if there's any idiosyncrasies in the way they do this work, we need to understand the aberrancy patterns and missingness within that specific data set. There are times when variables look similar, what to do about those. And the art of extracting and merging data is actually extremely important to maximize the potential of the data that you have at hand. So when it comes to EHR, what I realized really quickly when working with this stuff was that it's often not analysis ready. And we need to first synthesize data into information to make something useful out of it. And so in working with EHR data, I learned to go the extra mile. So know how the data is acquired, know how data is extracted, and how valid is the extraction method, or is there a validated algorithm by which you extract it? And what the question that's in front of you really is, does more equal to better? Of course, every time you do a data poll, you try to pull as much as you can in one shot, so you don't have to go back for more and wait forever doing it. But it's more always equal to better. And how analysis ready is that data? So what I mean is, do we have validated methods for capturing, extracting the data? Are we able to separate forests from the trees? And we need to know the caveats of each data set that we play with and know how to deal with them. So basically, missing this is an art. Is missing this at random? Do we know for sure if missing is at random? What I mean is, if we're talking about the STS, or the Society for Thoracic Surgeons database, I worked closely with surgical colleagues, and in fact, I led the group of data abstractors who abstracted the STS data, the part that surgeons didn't fill out. And very quickly, I learned when people didn't fill out something, for some people, it would mean that the patient didn't have the disease, and for others, it may mean something entirely different. So if you know that pattern, then you actually may not need to leave as much to multiple imputation. You may be able to fill the blanks more accurately and effectively. And just because it's not picked up doesn't mean it's not there. And there may be what appears to be redundant or conflicting elements that could be combined, but some may need to be removed to optimize variable capture. And so this slide is slightly redundant, and I kind of meant for it to be. And it basically talks about steps or at least the steps that I have been following in real life application. And so I would scope out sources of data that are available, and sometimes it creates it requires a bit of creativity. Knowing how much data is enough, I think is an art. And curating data into information, knowing what's really in the data set, and again, knowing the pattern of missingness. And finally, using information to describe challenges and find solutions, and definitely work with clinical colleagues, and working with a interdisciplinary team is an extremely important first step that makes sure that we go down the straightest path possible. And so why should we care? Because really data quality directly impacts the performance of our model. And, it's very easy to overtrain any particular model so that the performance looks overly optimistic when we're training or testing it on our data set. But then at the end of the day, the model that we built might just lack generalizability and doesn't really work in real life, especially when you apply it in a different setting. And so big data, bad data essentially goes into ineffective modeling. And so this is a really quick example of what we were able to do with data back at my previous institution, the University of Ottawa Heart Institute. And this was a model that we very quickly developed and deployed in response to COVID. And so basically surgical wait lists were mounting in response to COVID because we needed to free up beds, ICU beds for COVID as opposed for cardiac surgery patients. And so I developed actually a series of interconnected models to ensure that we're able to screen in patients who are at high risk of harm if they were waiting too long on the surgical wait list. And at times people were waiting for months for their life-saving surgery. And also at the same time, we had another algorithm to improve throughput in the ICU. And so the end result of using this for 2 years was that my center was able to perform the highest volume of cardiac surgery nationally during COVID, while still be able to accommodate the severe COVID patients, like the ECMO cases that were coming in. And so this is just an example of how data could be used and deployed rapidly with the help of software engineering and with the support of administration to effectively solve a problem. So thanks so much for attending, and I'd like to pass the mic to Dr. Edward Lee and Dr. Kristen Young from Stanford. So Edward is a postdoctoral scholar here at the Department of Radiology, and Dr. Kristen Young is a professor of radiology and of neurology and neurosurgery. And so Dr. Lee, would you like to load your slides?
Thanks, Dr. Sun. Great. Okay. Thank you, Dr. Sun. Hi, I'm Edward Lee, a postdoc at Stanford, working with Professor Young. I'll be talking about a proof of concept work of architecting and assessing the feasibility of a federated learning system across 20 plus institutions from around the world, touching all continents except for Antarctica, and using one of the largest, if not the largest, COVID chest CT data set curated by Dr. Young. We'll investigate not only the generalizability using accuracy, but also measures of privacy as well. We won't get too detailed into privacy today, but I look forward to having any questions answered by email or after this chat, after this talk. Significant advances have been made in AI systems, benefiting from the volume and diversity of publicly available data on the internet. However, AI systems for medicine reported in literature have had very little, not very little, but had exposure to relatively less data from less diverse sources. This difference in scale can be largely attributed to the fact that gathering data from many hospitals to one central location is not only time-consuming, but also poses some legal and ethical concerns over data privacy. Federated learning, or FL for short in my talk, is a field that enables learning across many hospitals without sharing private patient data. In this work, we demonstrate various FL methods on one of the largest and most diverse COVID-19 chest CT data sets. And we have here over 21 institutions with over 10,000 patients, 12,000 scans, and over 1 million CT images collected from around the world. FLS, so this block diagram shows the three main training methods that I'll be discussing. FL is shown in subfigure D, and this shows a high-level idea where instead of communicating sensitive data to each hospital, instead each hospital shares and communicates model grading information between each other. And so during the federated learning training process, there are these so-called federated rounds where each site performs a number of local epochs, training epochs on their own data, computes a delta of those weights tuned to that data, and shares those delta or those weights back to a parameter server where this server then aggregates all the weights from each of the sites, performs a weighted average, and broadcasts this new sets of weights back to all the sites to be used for the next round. There can be many rounds, and you can think of these rounds as kind of like training epochs in a normal training process. And usually the more rounds, the better, the convergence, and empirically, of course. There can also be more local epochs per round. And also there is another parameter, which I won't be discussing, but kind of instead of taking all the sites, so instead of taking all the sites per round, you randomly select to mimic kind of the stochastic gradient descent process. I'd like to also highlight that there are many other ways of performing collaborative learning, some of them that were developed here at Stanford, such as cyclical institutional incremental learning, or CIIL, and institutional incremental learning, or IIL. I'll be discussing those more in the results. This is a much larger expansion of our previous study where we show proof of concept using centralized data sharing. So here we show that there are common signals across all sites that could be used to differentiate between COVID pneumonias and non-COVID pneumonias. And the task is actually surprisingly difficult. There are cases, if you give the pneumonias and COVID positive cases to radiologists, some of them are incredibly hard to differentiate. For this current study, we have expanded our dataset diversity to include hotspots in Arizona that treated Navajo tribes, as well as urban Detroit that saw many of the African-American patients, as well as new geographic centers, such as from under-resourced communities such as North Africa and Tunisia, and rural Iran. And this has been an incredibly miracle work by Professor Young, who has led this collaborative endeavor. As a side note, we have also developed a mobile app that can enable rapid deployment and testing of any of the non-3D models. And so this app can potentially allow for educators to learn disease-specific AI features and report back to us on the feedback and generalizability on each of those sites. So we could tell really quickly how well our models are generalizing on their cohort. Now, just as a caveat, there are performance limitations on the mobile device. I'll talk to you a little bit more about that. To assess the success of FL, we must first establish the baseline performance using siloed training. To do this, we trained 20 AI models, so 20 AI models independently on each of the 20 sites, 1 to 20, as shown by the left. And all 20 models are evaluated on the holdout sites for each of the sites, as shown on the bottom. And by the way, we've actually also had external holdout site as well, but I won't talk to you about that on this presentation. All 20 models are evaluated on the holdout sites for each site, as shown on the bottom. And this represents 20 sets of training and 420 sets of evaluations. And here we see a wide range of model performance. First, almost all models have lackluster performance on virtually all the sites, and especially on site zero, which is the original China cell massive data set from China. So this was quite expected, as the images from this site from one class look really different than the others. For example, this China cell data set had normal lungs that were lung scraped, and while the other sites did not. The pre-processing was very different too. The images were very zoomed out compared to the others. And furthermore, in some of the other sites, some labels are missing, and there are considerable class imbalance and out of distribution issues. And while it is not shown in this talk, we do find that we can improve siloed training with pre-training from a site that has its data publicly available, and which is also, and it helps to have the data be quite large too. And data augmentation with synthetic data can also boost that performance. So we talk a little bit more about the data augmentation with synthetic data on this presentation. Okay. So here are the federated learning results. So federated learning on the training sets of 21 sites results in the following performance. We detail a mixture of FL strategies that include first pre-training on a public site, such as China Cells Site 0, using only synthetic data for FL, number 2, and using both synthetic and real data, number 3. So all FL experiments use an identical model architecture here. And with one local epoch per round, we observe 78% performance accuracy on average, and 80% weighted average accuracies across all the sites. However, we do find that even FL doesn't necessarily guarantee high model performance on all the sites, such as sites 12 and 13. And training with centralized data sharing, which is pooling all the data together and training a model on that, performs the best on average. FL with 4 local epochs per round achieves actually quite close to that CDS parity. Next, we investigate whether pre-training and data augmentation can be symbiotic and in accordance to FL strategies. So we take site 0 to be the public data set, which it is really. And with FL on sites 1 to 20 now, where the model was first pre-trained on site 0, we achieve accuracies that are actually quite close to FL on all the sites from 0 to 20. So it's actually not too surprising that that they're quite similar. We also propose a new method for data augmentation using synthetically generated data. And so to do this, we first train again on site 0, the public data set, and then sample on the site that we want to generate data for, as well as the class of label of interest. And one can see how if a site contains missing labels, the GAN can somehow impute missing data for missing training data that is consistent with the site's pre-processing and lung styles. After we train the GAN and generate synthetic data for all the sites, we train FL with only the synthetic data from each site, so no real data at all. So the performance as shown as indicated as SC in this figure is quite surprising. And this performance is actually better than any silo strategy, meaning if we only train FL on that synthetic data alone, no real data, we can achieve accuracies that are even higher than silo approaches. Finally, we examined the strategy using both synthetic and real data. And we see here that we actually see that this looks highly plausible. The performance is significantly better than using the synthetic data alone, and slightly worse than vanilla FL using all the sites from 0 to 20. But we also do notice that there are many sites such as sites 3, 5, 6, 8, 9, 16, 18, and 19 that improved from the vanilla FL strategy from all the sites. And we noticed that the reason why the average and weighted average accuracies dropped was that with FL training with synthetic data, site 0 performance fell as a result of its training data not being directly applied in the FL loop. So that's one of the disadvantage. Just for time, to summarize, pre-training and synthetic data generation do indeed help, but do not necessarily offer any significant advantages over vanilla FL using all the sites. But one may also argue that FL approaches are cleaner and easier to implement. But synthetic data generation does help boost performance over vanilla FL over many of the individual sites, and also grants the ability to perform quality control. Here, I'm gonna briefly talk about CIL and IIL methods. With these strategies, we have a model trained on one site, and then moved and trained on the next site, and then the next, and then the next, until all the sites are exhausted. And so this is known as institutional incremental learning. And with cyclical institutional incremental learning, this procedure is repeated many, many times. And here we report different path configurations on the left. And just to summarize, because of the highly heterogeneous nature of this of our data set, these path-specific methods do not converge quite well. For example, when the model comes time to train, on a site with some missing labels or there's some class imbalances, issues on that particular site, or let's say the site is completely corrupted, for example, with false data. I mean, hypothetically, the model performance worsens for that next site. So it could actually, yeah. We go over one of the proposed methods for boosting model performance with sideload and FL strategies. So this is data augmentation using synthetic images. And this was mainly motivated to handle class imbalances in the training and sideload FL strategies. So the GAN takes as input any real CT image from any of the sites and also a target class label that we want to synthesize. So the output is a kind of a deep fake CT of that particular site and label. And yeah, and that's how we can boost training data performance. So just some of the three things from this method. This improves many of the individual site performance, significantly improves the siloed approach, which I didn't talk about, and can provide researchers with a better handle on the QC of the training data, especially with pre-processing. And so on the right there, this shows a video of the synthetically generated images. And then lastly, and the last thing I want to talk about is this idea of heterogeneity. So there are some, an important theme in FL is the idea that FL can still be robust to non-IID data distributions. But the degree of IID-ness or heterogeneity can impede the performance of FL training. We investigate here the scenario where all the 21 sites had identical data distributions by first, by first pooling all the data and then randomly sampling, partitioning. And we investigate, we see that the accuracies are higher for the ID case, but only if we use a 3D model. And we see that accuracies are higher in general for the IID case over the non-IID case for virtually all the experiments. Thank you. I don't think we have time for privacy. And I'd like to now pass it on to, I believe, Michael, Dr. Mathis.
Yeah, thanks very much, Ed. That's a great presentation. So I'd like to introduce you to Dr. David Ouyang from Cedars-Sinai. And David is a cardiologist and a researcher in the Department of Cardiology and Division of Artificial Intelligence in Medicine at Cedars. He is a physician scientist with an interest in applying AI and deep learning in cardiac ultrasound. He himself is a sonographer. So David, you're up.
Hi, good morning, everyone. It's really great to be here. And thanks to Dr. Sun for moderating the session, as well as Dr. Langlotz and the rest of the kind of organizers for organizing this great conference. So I'll be focusing on talking about how to build infrastructure and getting data ready in uses in cardiology, particularly focus on echocardiography as I'm an echocardiographer. The outline is really kind of research, obviously some of the work that we can do with the data, but then a really description of that chasm in which we're seeing that there's a big gap between things that are kind of research ready or research described and really high AUCs versus what it looks like to actually get things into deployment and ultimately takeaways from our experience in running a clinical trial. So I'll speak particularly about cardiology, but I think that there's a definitely particularly focus on imaging, but you see that there's been tremendous progress in leveraging artificial intelligence. And this is true in radiology, dermatology, pathology, and kind of many forms of imaging of various sorts, and almost every modality, whether it's CT, MRI, PET, or even things like waveforms, that's EKGs. I focus on echocardiography because it's one of the most common forms of cardiac imaging. It's about kind of 10 to 20x more prevalent than cardiac MRI or cardiac CT. And as we know in artificial intelligence, we are still very much in a paradigm that more training data ultimately leads to better performance and leads us to more robust models. And I think that this is an area where echo, being frontline cardiovascular imaging, really has a lot of opportunities and really is a place where there's a lot of great research that's happening. This is just one example, but in 2020, about now almost 3 years ago, James, Ewan, and I published work, and we used kind of video-based models for assessment of left ventricular ejection fraction. This is the most important metric we look at in echocardiograms, which is how we define heart failure, our assessment of response to therapeutics, our understanding of kind of the state of a patient, particularly if one's in, say, shock and you want to have a firmer sense of its cardiogenic versus distributive shock. This echo is really helpful. But we published this in Nature now 3 years ago, where we use kind of these models for segmentation as well as regression to the ultimate ejection fraction. This is an area where we are very excited, and we show that there's great performance both at Stanford as well as at Cedars, which was an external validation site. But ultimately, this is an area where most of the work in this paper is still retrospective, is still on cohorts that were defined from cohorts that we derived from the EHR or from our PAC system historically, and wasn't an exploration of what it looks like when it's actually in clinicians' hands. So this is what I mean by the chasm. I would say that kind of the impetus of this conference, as well as many others, is really showing that there's tremendous opportunity and excitement in artificial intelligence. These days, there's a lot of excitement in large language models, but continued excitement for convolutional neural networks, kind of many other different kind of architectures, but really applied to medicine. We see that there's a lot of variation in medicine, and we're hoping that AI is a way to streamline, automate, and make things more precise. That said, despite all this great research, and despite the fact that we see high performances on most research papers, for most of these models, they're not quite at deployment. And I think that, as some of the previous speakers referred to, I think Dr. Lee and Dr. Yong was described, is that some of it might be questions about data sets, that given patient privacy, people might not be able to share across institutions. And with small data sets, the performance is not as good as with larger data sets. But also there's a question of what does it look like to pre-process the data? There's questions about how the pre-processing has an outsized impact on the ultimate models as well as training, as well as deployment. How do you actually integrate the model outputs in a meaningful way, or in a way that clinicians can use and can be impacting patient care? And the example I give is that kind of I typed in healthcare system deploys artificial intelligence. You know, there's about 75 million hits. But that said, when I kind of in my clinical practice, when I see AI models, I really don't see that many in clinical practice. I think that there's a lot of hype and there's a lot of hope, but ultimately of things that are either FDA approved or actually in deployment, it becomes a much smaller number. And part of the reason is that, along with researchers, the regulatory bodies are also learning what is the bar, or how should we assess these models. Obviously, there's a lot of news about brittleness, about bias, about many other potential pitfalls or caveats with models. But really, right now, the regulatory landscape continues to evolve. And one example I would give is that we published this paper now last year, in that of the AI models that had been FDA approved, very few of them have been shown for performance on multi-center sites. The vast majority are only evaluated on retrospective data, so historical data. Almost none, or essentially none, are randomized, and essentially none are blinded. And I would say that, as clinicians in the audience know, these are the thresholds that we use to assess whether a therapeutic use is useful. It would be weird for a drug company to introduce a new therapeutic or a new medication without going through prospective, randomized, and blinded trials. And for better or worse, right now, that's not the bar that's needed for a commercial deployment of an AI system. So as part of an effort to really rigorously assess our model, even though it's already been published, we wanted to actually design an RCT. This is actually an RCT that was performed this past year at Cedars-Sinai. Our really things that we think are valuable RCTs is, in addition to the fact that it's prospective, where there's less of a chance of cherry picking data, we wanted to design it in a way that's blinded. So people aren't biased towards whether it's AI or not. We wanted to randomize to potentially balance out unknown confounders. And we also wanted to actually compare with an active comparator in a true clinical setting. So our study was a single center study. We actually asked for sonographer initial assessment. So our sonographers have a mean of 14 years of experience. And then cardiologist essentially overread, or cardiologist reporting or adjudication. So kind of this study used 10 cardiologists with a mean of about 13 years of experience. Because this is the standard clinical workflow, we wanted to embed our AI system in a way that mimics this and hopefully can be blinded to this. So the way that we designed our study is that sonographers obviously are the ones scanning the patient, and our model only assesses ejection fraction. So at the point of measurement, usually on a computer system at the PACS, we randomized to either the sonographer assessment or an AI assessment. And then this is blinded, and the cardiologist will be asked to evaluate or adjust in their usual format if they disagree or want to change the ejection fraction. I would say that there's 2 points to point out. One is that there is a run-in period. Their sonographers had to be able to measure these echoes. You can imagine that there's a range of echo quality. If it's sufficiently low quality and the sonographers can't measure it, neither are we putting this into the trial. And also the primary outcome was what was the proportion of studies that were actually adjusted more than 5% by the cardiologist. And a big part is that we did this actually in our clinical PACS system, which is kind of Siemens. And a big part of what we did was trying to make sure that it is truly blinded. So this is work done by Brian He, kind of one of the Stanford PhD students, which actually you can see that our model on the top left looks like it can trace every frame and every beat, but we don't necessarily want to show that to the cardiologist, because then they would know which tracings are done by sonographer and which tracings are done by AI. We actually mimicked what the sonographer usually does, which is only measure one beat of the ejection fraction, and then only show that representation so that cardiologists can't tell. So this is what it looks like. This is Siemens. This first tracing is done by a sonographer. You can see that when we click on the tracing, you can actually see in green the tracing of the left ventricle at systole and diastole. It's a user interface that allows for adjustment, but here we're actually running some computer code so that we introduce the AI tracings. And you can see that going back to the same image, we don't delete the previous one in this setting, but you can see that there's 2 new tracings. And these tracings are actually done by AI and in the same, I think, system, so that we can show cardiologists only one of the 2 and then ask them to assess in a way that hopefully is more blinded. And additionally, our trial was actually done on historical scanned images, so that we also wanted to test the efficacy, or in addition to efficacy, but the safety of the AI system as well, so that we do have the historical echo report that has an ejection fraction, and we wanted to see how much of variation there is with AI guidance. And also, if we actually just use the arm of the trial that was sonographer guided, we would say that this is the largest study of test-retest for echocardiography ejection fraction. The other studies have done it on the order of 100 patients, but our study actually has 3,500 patients. So 3,800 or so echoes were assessed for eligibility. About 5% or 5 to 7% were of insufficient quality to have kind of tracings of the ejection fraction, and about 3,500 were randomized, run 1-to-1. And you can see on the right-hand side, I won't kind of belabor it too much here, but this is the distribution of the kind of baseline demographics of the patients that underwent echo. And first, I wanted to actually talk about the blinding before talking about the primary results, because I think that this is important. Really, there are very few blinded clinical trials of AI. On one side, you see that there's a set of tracings done by AI, and one side there's a set of tracings done by sonographer. They're shuffled across the rows. I'll give kind of the audience a moment to take a look at it. But in our clinical trial, we asked the cardiologist to assess, do you think this is done by AI, or do you think this is done by sonographer, or can you not tell at all? And in general, cardiologists could not tell. So they were correct, meaning that it was AI and they guessed AI about a third of the time. They're incorrect about a fourth of the time, meaning that they thought it was AI, but it was actually a sonographer or vice versa. And about 45% of the time, they just ultimately said they didn't want to check, or they thought there was insufficient evidence or information to tell which one it is. So this calculates out to a blinding index of 0.088, which is considered good blinding. Good blinding is between negative 0.2 to positive 0.2. And in this blinded setting, we actually saw that there was significant improvement and benefit with AI. So substantial change, more than 5% change in ejection fraction happened in about 17% of the time with AI versus 27% of the time with sonographer, which was actually a p-value of less than 0.001, both for superiority as well as non-inferiority, because the trial was designed as a non-inferiority trial. And this actually resulted in that showing that cardiologists were actually less likely to change the AI tracing. And that compared to historical tracings that were not guided by AI, using the AI actually made cardiologists more consistent, so that it's about a 6.3% change in EF versus a retest versus a 7.2% change in EF versus kind of with sonographer, again, the human test accuracy or precision. And we have some outcomes showing that this saves cardiologists as well as sonographer time. But really, the main takeaways as we talk about kind of AI deployment as well and integration is these two main takeaways. First, ultimately, for most AI models, we still need a lot of training data. And I always say that I think if we look at training data across kind of AI in healthcare, many kind of both research projects as well as commercial offerings are being trained with on the order of 1,000 or maybe 10,000 at max studies. We saw that kind of from our assessment is that there is really no asymptote, and that you or anyone designing AI models for healthcare still have outsized benefit if the models are trained with more and more data. For example, our clinical trial actually used about 150K echocardiograms, and that from our benchmarking, this actually had better performance than our previous Nature paper model using only 10K studies. Second, a really important part of our study is the ability to deploy into the PACS system. So in addition to read access, where you have data, write access, where you can actually integrate into the actual clinical PACS or actual clinical system, is really important. And this is something that I'll probably end on, but mostly focus on, is that this has a lot of important aspects where it needs an engaged hospital IT team, it needs a collaborative industry partners, the PACS vendors, and it needs clinician buy-in to do this. And that's actually ultimately one of the highest lifts, kind of having that combination of three at a medical center that really drove this project forward. And finally, currently, for a lot of what we're currently exploring is going through to the FDA with this data and actually allowing this model to be deployed actually across the country. But I just wanted to say thank you, since this is about 15 minutes, and we'll chat a little bit about this during the panel discussion.
Thanks so much, David. Perfect timekeeping too. So I'd like to introduce our last speaker, Dr. Michael Mathis from University of Michigan. So Mike is a cardiac anesthesiologist and a data scientist. He has research interests in using what I like to call big data techniques and apply it to perioperative hemodynamic data. He's a research director of the MPOG group. Welcome, Mike.
Thanks, Louise. I really appreciate the introduction. It's humbling to be a part of this panel, and just fascinating to hear what everyone has to say. This talk will, as you heard from the previous speakers, some of this is not just about the complexity of your AI model, but actually just about the quality of your data. And that's what we're going to double down on in this talk, is data quality and doing it effectively, managing issues related to data quality effectively at a multi-center level. I have no personal financial relationship with any vendor. My work is supported through the NIH and Department of Defense. So as Louise mentioned, I'm the research director for MPOG. What is it? It's and how does it relate to this conference? Well, it's a collaborative of over 50 hospitals across the US. We use perioperative data for any case requiring an anesthesiologist, and it's amassed into a central database housed at the MPOG Coordinating Center at University of Michigan. And with appropriate protections and data governance policies in place, it's been used to perform multi-center outcomes research, as well as quality improvements with precision performance feedback emails sent to over 7,000 anesthesiology faculty, residents, and nurse anesthetists across the US each month. Here's a broad picture of the data flowing into MPOG. The unique strengths of the MPOG database are its granularity. The operating room is arguably one of the most well-monitored settings in all of healthcare, with minute-to-minute vital signs, medications, intraoperative interventions tracked, enabling new insights to be made along the perioperative trajectories of patients. And given the richness and quality of this data, it presents a unique opportunity for machine learning and AI-based methods to understand patient perioperative care trajectories. Really, to get at this granular data, you need complex methods to handle, big data to be used. But of course, the struggles that I have as a clinician helping direct the research within MPOG, the struggles that MPOG has in deriving meaningful clinical inferences from messy real-world electronic health data aren't unique to my specialty. They transcends any clinical specialty, and these problems include the issue of non-standardization of data. So how healthcare is documented at one institution might be different at another institution, even if they have the same software vendor. The volume of data, again, so in the anesthesia record, we have minute-to-minute data, and that can really increase the scale of your database. If you look at waveform data, again, you're talking about 60 to 240 data points a second for each waveform. So it's just the issue of volume. There's also the issue that physicians aren't considering how electronic health data will impact research and QI. They're just using it to impact patient care, as they should be. And so, physicians are fundamentally busy people, and it's not a valuable use of their time to ensure electronic health data is tidy and curated. And so these are the challenges that we're facing if we're going to do large studies using real-world electronic health data. And so for any multi-center data structure, so to be able to have a multi-center data structure in place to perform any kind of research or QI initiative, let alone one that uses machine learning or AI, there needs to be a pipeline for data handling, including steps for scrubbing PHI, mapping EHR concepts into interoperable terms across sites and software vendors. We need to filter out noise, and we need to democratize the access to this data to practicing clinicians. So this slide shows just our own pipeline within MPOG, which can be, again, translated to any clinical specialty doing multi-center research and QI. And this is obviously a busy slide. Can't possibly cover all the details in 15 minutes, but I'll highlight 3 key challenges and strategies that we've taken within MPOG to address those challenges that are translatable to any other clinical research or QI application. The first one that I'll focus on is our strategy of EHR concept mapping used to address the challenge of achieving semantic interoperability of data across sites and software vendors. To illustrate this challenge, consider an example of studying how cardiopulmonary bypass is used for cardiac surgery across anesthesia records using in 3 different hospitals, each with a different software vendor. Since each software vendor has a different way to document the start and stop times of cardiopulmonary bypass, we need to create some tool that compares apples to apples. We created this tool that each site joining MPOG uses that maps their local EHR concept, so that you can search for the word bypass in your local EHR, and we can map those to universal, semantically interoperable multi-center concepts that can be used, again, to compare data across sites. And this is one of the steps that we have for onboarding any site into MPOG, whereby we give each site a list of the universal MPOG concepts, and then we have trained clinicians at each site go through the process of identifying their local EHR concept equivalents. So the end result is a multi-center repository of standardized concepts that enable multi-center research in QI. But of course, just going back to our pipeline, the story doesn't stop here. And although we've converted all EHR data to the same language, we really haven't addressed issues yet related to the messiness of EHR data. And so if you're a clinician in this audience, you know very well that real-world electronic health data has issues related to missingness, redundancy, inaccuracy, that requires you to not put too much trust in any one data point, and instead you derive a clinical gestalt from seeing the totality of EHR data for any patient and having a deep understanding of the strengths and limitations of different kinds of EHR data. And so we need to replicate this, this kind of clinical intuition if we're going to use EHR data effectively for multi-center research. And so within MPOG, our strategy has been to develop clinical phenotypes based upon messy raw EHR data. What is a phenotype? Well, broadly, we're taught that a phenotype is a composite representation of individual observable traits. Here's a picture of an animal that has 4 hooves, black and white stripes. It roams the plains of sub-Saharan Africa. When you put that information together, you arrive at a high confidence inference that this is the zebra phenotype. If you apply this principle to electronic health records, phenotypes are, again, a composite representation of patient characteristics or clinical events manifested in the EHR. So, for example, if you had a patient who has on their medication list an oral hypoglycemic agent, or if they have multiple serum glucose lab draws that have a glucose that's very high, or they on their medical problem list, you see diabetes, you can be more confident that this patient truly has diabetes than if you had only known about one of those 3 pieces of information. So that's the EHR phenotype. Just give you one more example in the anesthesia context. One of the things that we've been challenged to do in MPOG, and it's very common in any research or quality improvement measure within MPOG, is we're asking the question, is this patient under general anesthesia? Here's a picture of a patient obviously under general anesthesia. When I walk into this OR, there's no question that this patient is under general anesthesia. But the EHR representation of general anesthesia can be more nuanced. And what we've done within MPOG is we've looked at whether or not there's any documentation of an advanced airway in the patient. We've also looked at what medications the patient got. So if you got a neuromuscular blocker or paralytic, that's obviously a patient under general anesthesia. And we look at ventilator data too. If you can detect exhaled volatile anesthetic gases, that's an indicator of general anesthesia. And so, we take these EHR clues individually, any one of them not giving us perfect confidence, but if we kind of list out all of the data that comprises these clues, and then take these standard concepts, we put them through kind of a logic circuit board, which in some cases can use AI and machine learning based principles. We can spit out these higher confidence phenotypes. We have the general anesthesia phenotype defined by higher order reasoning applied to messy electronic health data. And then importantly, for any time that we're going to do a research or quality improvement project using the general anesthesia phenotype or any other phenotype, we're not going to reinvent the wheel. We're going to use these and reuse these as Lego building blocks for future research and QI interventions. And we're going to maintain these phenotypes, making sure that the quality of them doesn't degrade over time. We need to re-audit and revalidate these phenotypes continuously, because we all know that EHR data, the quality can shift as practice patterns or documentation patterns change over time. Phenotypes aren't something unique to MPOG. It's a principle that's translated to all healthcare specialties. A good repository of EHR-derived phenotypes can be found at vkb.org, so I just direct you to that website. And finally, a third challenge here is, although now we have a way to get EHR data translated into the same language and then spun up into a higher order clinically useful phenotype, we still need to address the issue of democratizing access to frontline clinicians. So we need to make MPOG data accessible to clinicians who may not have a master's degree in computer science and might not be a first-degree relative of their hospital's chief medical information officer. We want to address this challenge through a couple of different tools. One tool that we've developed within MPOG, again, translatable to any other clinical specialty, is a user-friendly tool called Data Direct, in which a clinician can use intuitive filters to create a cohort of patients to study, and with appropriate IRB, DUA, and other regulatory approvals in place, can gain access to a limited data set with identifiers removed to do a high-quality multi-center research project. And here's a fictional example that I created, just creating a cohort of patients that you can very quickly understand within MPOG how many adults undergoing emergency cardiac surgery received epinephrine intraoperatively, and we can get to a case count that can be used to inform the feasibility of a multi-center research project. And then again, with appropriate regulatory approvals in place, you can get a user-friendly Excel spreadsheet or whatever other form you'd like it in to see this data. On the QI side of the equation, we've democratized access to performance improvement data through the use of MPOG specific perioperative quality measures based upon existing high quality evidence derived from MPOG and derived from MPOG phenotypes. So for example, a quality measure might be how often did you check a hematocrit after transfusing a unit of blood. These QI measures can then be amassed at a site level where a quality champion at each MPOG site can review site level performance on a quality improvement dashboard. And also QI measures can be distilled down to the individual clinician level, where each clinician participating in MPOG, the 7,000 anesthesiologists, nurse anesthetists, and residents participating in MPOG, they get a monthly individualized performance feedback email describing their performance on their last month's cases. So that brings me to the conclusion of this talk, which is that EHR data is messy. We all know that, but it can be used for good, provided that you have ways to map multi-center data to universal concepts that helps tackle the interoperability issue. And then the messiness issue. So digital phenotyping is one way to mitigate the problem of garbage in, garbage out. You need to have a higher confidence, clinically useful data to do research on. And the second take-home point is that accessing multi-center data ideally should not be 95% of any researcher or quality improvement champion's effort. We need to create tools to democratize access to data to enable rapid research, and we need to offer precision feedback platforms to QI champions and individual clinicians so that you can rapidly adopt and iterate upon clinical performance metrics. So with that, I thank you for your time, and I'll turn it back over to Luis and the panel discussion.
Thank you, Mike. That was a great talk. And thanks, everyone. We're at 9:01. We're precisely on schedule. So I'll ask all the speakers to please turn their cameras back on. And maybe we'll just start to address some of the questions from the audience. And for those in the audience, please do feel free to type in your questions. We'll be monitoring them. And so maybe we'll just start from the beginning here, and we'll go around the table. So we had a diverse range of speakers this morning, and we all talked about different aspects of data and AI in cardiology, in radiology, in anesthesia, and in administrative or operational management. We have a question that actually goes back to the basics of what the definition of big data is. So the question reads, is there a cutoff data size for data to be called big data? Maybe I'll skip over and be one of the last ones to answer this question. Anyone from the panel who wants to tackle it first?
But I mean, there may be some rigor. I mean, there's a rigorous definition here too, but I think a lot of it just comes from just functionally speaking. Big data is any data set that a kind of a traditional computer processor would be unable to handle, and it's usually whenever you find yourself using tackling a data set where whatever traditional computer program you're using to analyze data no longer works, that's when you've entered the realm of big data, at least from like a practical standpoint.
For sure. Anyone else? Ed, what do you think?
I would consider it, well, big data has been around, I guess we've been working with big data even before deep learning, but I think with deep learning, from my perspective, big data kind of comes to mean that if you throw as much data as you can, more data is always good for the model performance. And generally, training a model with an N of 1,000 versus 1,000,000 is not necessarily any different in terms of the difficulty. And so I feel like with deep learning, there's some degree of skill going from small data sets to massive data sets. I guess that's where the context of big data comes from my perspective. But I guess going back to the original question of cutoff, I think this really depends on the domain. I mean, if you think of natural NLP, each datum is quite small in terms of data set size. You know, you might have kilobyte per sample, but in video or images or video, 3D images, you could have massive gigabytes or even terabytes for a small number of patients or unique people. So there, the question is big data can mean the sheer size of data in terms of the gigabyte, the information, the number of bits encoded to encode this data, or it could mean the number of unique patients or identifiers. So I guess
Yeah,
that's
I completely agree with you. I think in a way, we're not just dealing with the number of rows in a data file. It could be for just a large number of data elements for a small number of patients, and it really depends on computationally what type of work you're trying to do. Let's see if David and and Dr. Yang agree with us.
Yeah, I was going to say I very much agree with Michael's definition. Ultimately, like if you have to use Hadoop or something that's distributed to process the data, that's the reason why people talk about kind of cloud infrastructure or stuff like that. If I had to say realistically, a lot of medical data sets might not meet that definition, right? Imaging aside, which tends to be large, a lot of structured tables can be handled quite well with a local laptop. And we colloquially describe it as big data because obviously it's still a lot of patients, but might not need the specialized tools that really kind of really it is deserved on really large data sets.
Totally. Kristen, what do you think?
Yeah, I mean, even across imaging, we're going to encounter different data sets and data sizes, right? If you're looking at chest X-ray versus even CT or 3D acquisitions on MR, which in itself has multimodal, multiple sequences, even for one patient, we're talking about thousands of images and different ways of parameters, right? Like diffusion and T2. You look at all of that, even one patient has massive data really per patient, right? But then we do want that heterogeneous data. We definitely want to scale across different centers and across different countries. I mean, it's really remarkable. And so I think it really depends on what you're targeting. I think even with the smaller data set, you might be able to find meaningful signal. And sometimes even within image, I mean, so I think it really depends on what you're trying to tackle and answer, but there are different ways to kind of, I think, see, how you define big data, right? Like even one patient, there's tons of data you can mine that we were unable to prior to advent of deep learning and so on. And so, but certainly we definitely want more patients, I think, the better.
Yeah, definitely. And I think, that applies across the board, regardless of what type of data science project that we're tackling. We definitely want to have more rows in our spreadsheet or have more N's in our sample. And I think, the definition of big data is very much a philosophical question in a way. And like all our panelists are saying, I think it really depends on our needs. But ultimately, we like to use the term big data to describe the integration of a variety of data sources in order to achieve the end result of precision medicine. So, and everyone, please keep the questions coming. Those are great questions. The next question are, let's see, what are the pros and cons of using federated learning? So it looks like Ed and Kristen question.
Yeah, so I guess the biggest con is challenge for FL is heterogeneity. Doesn't necessarily answer that question. Any model trained with FL does not necessarily guarantee that it'll work on all the sites data, irrespective of the size of the data. And if there are sites that are completely out of distribution, it can actually negatively affect the FL model performance. And to even go beyond that, you can have adversaries in this network where they're injecting bad data here and there every now and then, unknowingly, and it could adversarially affect the final trained model. So with FL, it kind of democratizes the training process by having pushing the control to the end users and the sites, the clients, and less on on one institution or site. But because of that, we give up quality control in terms of the training process to some degree. Yeah, and furthermore, so that's one of the big challenges. Another challenge is communication. When you're doing a lot of these federation rounds, like let's say 100 to train one model, and let's say you have 1,000 sites, for example, then you're sending equivalent of a model per round from each site to one location. And so this could place huge bottlenecks on not only the training per site, but also the communication between these sites. You could have bad network connections. You could have, for example, Tunisia. Do they really need to send their model 100 times and synchronize back and forth to train one model? Yeah, so I guess those are kind of the two main challenges from my perspective. But the pro is that it kind of goes back to the idea of why we do FL in the first place is this allows us to train a model without sharing data, and that's a pretty great thing, and do it in a principled way. And another, I guess, going back to one of the challenge is the third challenge is with FL you still need a central parameter server, so there is still some centralization needed to occur, unlike cyclical institutional incremental learning or IIL, where you go point to point. For FL there is centralization, but not with data, but with model information. So, and hence the term federation. Yeah, I guess that's from my perspective. If Kristen wants to add.
Yeah, I think I covered most of it, but I mean, the benefit and the idea is that we can possibly achieve this without necessarily sharing data, which is, has a lot of, which we encounter privacy issues and, I mean, how do we even scale that sometimes that there's some issues in the medical domain. But what we've learned in our experiments is that it's not always rosy, right? Because let's say you train at Stanford and we want to move it over to Michigan. Well, we hope it helps, but we could be even polluting, bringing in bad stuff over. And we found out it really depends on especially when we do the cyclical thing or incremental thing or whatever, when we go from the prior, where it was trained from the prior site makes it also could impact, right, on how it does on the next site. And then, of course, we also have to think about model forgetting. Now, I don't know if you had a chance to talk about that, right? As you move onward to other sites, that there's some form of forgetting, right? Like loss of memory. So I think they're all, again, so in concept, I think it's really exciting, right? But we certainly, in the medical community, I think we need to investigate this, partner with our collaborators. And before we adopt this, hey, it sounds great, let's do it. We really have to know what are the pitfalls, where are the challenges, do we really trust this? And maybe, so again, that needs to be, tested and vetted, I think.
And just to add to Kristen's point, federated learning doesn't solve privacy necessarily. This field is so massive and so ripe for exploration. And there are recent works where, recent successful works where you apply, for example, differentially private mechanisms to sanitize private data before you do federated learning. There are works where with federated learning, you're exposing more patient data, more information about the patients than even the centralized data sharing. So FL doesn't necessarily solve privacy per se, but it's certainly ripe for research and exploration, extremely ripe.
Right, and thank you. Those are really excellent points, Ed. And going along those lines, we have another question from the audience saying, how do you preserve patient privacy in federated learning when you're sharing data between different nodes?
Yeah, okay, so I guess to answer that, you have to define what privacy is. And there are a couple of ways to define privacy. If you look at the theoretic measure of privacy, you compute privacy bounds, more of the theoretic bounds using statistics. You can empirically measure privacy, which we did here with membership inference or even model inversion. So model inversion is given a model, you could do backpropagation on that model to get back an image that's representative of that model, what that model was trained on. Membership inference is kind of a traceability attack where an attacker, given this model in a black box scenario, can determine whether a piece of data or a patient data is part of the training, was part of the training process, and therefore know if you or I or anyone was part of this training process. If it was trained on a cancer model, then there's a high chance that I know something about your cancer history potentially. So first of all, I guess I just want to point out that there are lots of measures of privacy, and but I guess the standard way of preserving privacy in general is with DPSGD or differentially private SGD. I guess that's kind of the de facto way. So with DPSGD, what you do is let's say you have a federated network. You train locally as before on all the sites, but you do that so you replace the SGD optimizer with SGD plus clipping and noise. And with clipping and noise, you can get better privacy bounds, lower privacy bounds, delta epsilon measures, while and ultimately what you get is a Pareto optimal curve that shows the trade-off between how much privacy you're willing to accept versus the accuracy or utility of that particular model. So if you add in a lot of noise to the DPSGD process, you can achieve higher privacy loss, better privacy loss, but give up the accuracy of that final model. So I guess that's one way. But what we see from DPSGD with that is that we're actually non-fed as well. Is that DPSGD actually it severely degrades the performance of the model, and I think right now what we need to do is find a better measure of privacy that's more that's closer to that has tighter bounds rather, instead of assuming just an exponential family of data distribution, assuming something more about that particular data.
So
it sounds a little bit kind of hand wavy, but
So I just wanted to kind of maybe reframe some of the federated learning discussion and definitely kind of Kirsten and please let me know if you feel differently. But in many ways, federated learning is a technical solution to a social problem, right? The social problem is which you can't share data. That doesn't mean that it's not an important problem, but it's how do you build models when that's constrained? And I would say that kind of this is unique in some ways, very unique to healthcare, or kind of research projects are premised on healthcare because there's such strong patient protections, right? If you look at OpenAI or Google, they're not using federated learning for most of their stuff. Like if you look at large language models, that is not done in a federated setting. And the challenge is that privacy is so important, is that kind of this technical solution, even though it's called kind of privacy preserving, it's a technical definition of privacy that might mean something very different from what you and I think of in terms of privacy. That the quantitative privacy is actually a very different construct, and that's where kind of I think what Ed is describing is that there's many different ways to describe privacy and have ranges of privacy, but that ultimately means something very different from, oh, I don't want people to know that I'm this person.
That's right. So, I mean, even if we scrub patient, date of birth and name and address and all of that, which we do, you can ultimately find something about the data, and we can back propagate and say, you know what, this data set we think came from Stanford, or something about that population cohort. And so that's what we're talking about, like a technical terms of like the privacy bounds of the data, I guess.
Yeah. And in some ways, it's intuitive that if a model gets smarter in learning about some going from data to decision, then it's intuitive that this model that you can learn something about the model, what the model was trained on. It's quite intuitive that model performance and sensitivity to the privacy sensitivity, they go hand in hand. But how they trade off depends on the type of algorithm that you use, the type of model that you use. If you use a very large capacity model and you completely overfit to that data, then chances are that with membership inference, you can have 100% accuracy of determining whether any patient or a particular patient was part of the training set. So yeah, that I guess that Pareto optimal frontier, that really depends on the type of model, the training process, even the type of data being used.
Definitely. Thank you, everyone. Those are great answers. And I just love that, the clinicians are able to put an alternative angle on the explanation to the privacy problem. And so I think, the so-called privacy problems are actually not unique to just federated learning. It's actually pretty applicable to every time we have a multi-center registry, or when we have a consortium of different sites. I think even with administrative data, where we only mark the sites as 1, 2, 3, 4 and just label them with a unique identifier, I think there's also always concern with back calculation and privacy issues that could result. And so actually going back to all of the data and the innovations that we could do with data, another question from the audience was actually, how do we deal with potential intellectual property issues that arise when we start to navigate between vendors? The question was directed at David, but please, everyone in the panel, Mike and the others, please feel free to chime in as well.
Yeah, it's a great question, and it's definitely, I think, something broader than any particular project. Is like, how do researchers and academics work with industry partners, and really kind of what is the kind of aligning North Star and how to work with people. Ultimately, our goal is to, or at least my goal, and I think that it resonates with probably most of the panelists here, is we want to see technologies actually impact patient care, or in the hands of clinicians, or in healthcare deployment. I would say that I think the IP side actually, in my view, is actually less important. Kind of one, there's a lot of controversy about software IP and patents. There's already kind of a relatively gray area. Two, if we look at the tech space, most of what's valuable for a lot of these models and architectures rely more on the underlying data as opposed to particular innovations in terms of the architecture itself, right? This is true for CNNs, and kind of if you kind of try various kind of architectures, they'll probably perform very similarly. And this is also true for large language models where, you know, the architecture is very similar. I think in some ways, I imagine that it'll be more of a trade secret type of framework where there might be certain ways where you think that your model is really great because of this particular thing that you did in training or in deployment or something like that. But ultimately, I think that this is a area where we're fortunate that most of the intellectual property per se is actually very open. And I think that's some of the strength of software and why it develops so quickly, is that people can build upon one another. Our model from the Nature paper in our code is open released. And I think that we're very happy to have it open released because it's something where we already see that people build upon the data sets and build upon the models. And even in that settings, vendors are happy to have these kind of models integrated, and I think work with kind of people who want to do kind of AI models in healthcare.
Thank you. Mike, have you had a run-in with intellectual property issues?
I mean, I think you know, I agree with everything that David had to say. And you know, my own experience is basically you know, as soon as this is on your radar about, you know, developing something, that's the time to have that conversation. You can never have it too early. And a lot of times the conversation just revolves around, yeah, what is yeah, how, you know, is this, you know, what is your goal? Is this a you know, is the product that you're developing, you know, is your goal to just add to the scientific community as best you can, and you would, you know, welcome those who are able to contribute, in which case you'll probably have, you know, it's not just about patenting, it's also just about, like, you know, your licensing of your tools, and you may have some, yeah, open source. You generally lean towards open source in those situations. If you're, you know, if your goal is to have, you know, job security or profit, then you need to have more restrictive patents, obviously, and there's a balance here, right? We don't you may still want to be contributing to the scientific community, but you would be upset if your product, if somebody and maybe you're not seeking profit yourself, but you'd be upset if somebody you know, with access to your tool used it to profit for their own, you know, for themselves, then you might have a different kind of license for that. And so there's this tech transfer issue and different kinds of licensing that are, you know, more open source versus more restrictive. And really, it's, you know, you can't have that conversation too early. It's generally good to do that. And there's usually at each, you know, at academic institutions, there's usually an office of tech transfer that you can talk to. And we've certainly done that.
That's a very good take-home point. Kristen and Ed, do you have any experience with this?
I guess I could, yeah, well, we talk with Office of, I guess, OTL, isn't that what it's called here at Stanford? Yeah, and sometimes, you know, I've had vendors approach us too, like, hey, you know, we read your aneurysm model or this or that, and we want to adopt it in some fashion. How do we go about it? And I think, you know, at every institution, you can talk with the OTL team and kind of try to navigate from that perspective. What I did find difficult, and I didn't, you know, like I didn't actually pursue that avenue, was I found it difficult because at the end of the day, there was some request, well, we actually need the data that you use to train commercially to retrain. And I just, that kind of seemed a little bit, I don't know, like a little hard for me to navigate through and when this all began, that was what, 2018, and none of us really knew how to deal with that. Actually, the OTL didn't know how to deal with this. This was a little bit of a brand new territory for us at the time, 2018. And so, but I think maybe things that have come farther, I don't know, maybe Louise, you and David and Mike, you guys and Ed have different perspectives on this, but we found that I personally didn't pursue that, but I think that conversation has occurred, right?
Yeah, you know, it's
It's
amazing.
not
how-
just sharing your algorithm. It's a kind of
Right. Yeah, I totally hear you. I think it's amazing how the health tech industry has exploded over the last few years.
right.
Yeah, just in terms of number of patents and inventions that we generate, and just the type of stuff that we can do with data nowadays. I think every year is a new year mark that we can use to benchmark our performance. So we do have a couple of patents, and I think it has to do with did you generate the invention yourself from an academic institution versus is it an industry collaboration to begin with? And so I think, implications for patenting and for ownership of the intellectual property starts off a little differently depending on the scenario. And the next scenario is once you're ready to commercialize the invention, how does it work, right? That's where we really need to talk with the tech transfer office. And that's where we really need to sort out, not just the ownership of the patent, but also we have 1 minute left. So but we could we could, we could pick up this discussion, I think, at a later time. Okay, let's see. Has anyone attempted to do training using encrypted data? We have 30 seconds to answer this question.
Oh,
That
yeah,
will be the last question from the audience.
yeah, there are works, but I don't buy it. I'm not an expert, but I don't think it's possible. I mean, I don't think it's realistic. Training with homomorphic encryption.
Anyone else from the panel?
But
Mike and David?
I have not.
Yeah, it's a tough problem. It gets into the privacy issues again, and so it's just, yeah. And then there's the issue of synthetic data. Tough thing to address in 30 seconds.
Yeah, we have experiment with the synthetic data, but it's it's interesting. But
Yeah, there are actually vendors that sell software that generates synthetic data nowadays. So definitely lots of things to explore. But I think this could easily turn into a 2-hour panel discussion because there's just so much to talk about. And I would like to thank all of our speakers for their excellent contribution to our session. I'd like to thank the audience for attending our session and for all the interesting questions that were raised to facilitate our discussions. Thank you.
Yeah. Thanks, everyone.
Thanks, everybody.